Hello, ladies and gentlemen. This is Dean from Waffly Pi, and this is linear algebra. Remember when we talked about some transformations being linear, and I said that t of 0 always has to be 0? Well, some transformations make certain vectors into the 0 vector that aren't the 0 vector as well. The list of them is described by a vector space, and remember vector spaces always include the 0 vector, called the kernel of the transformation, which is denoted ker t. The kernel is a subspace of the domain, so any vector that transforms into the 0 vector obviously has to be part of the domain. When I was in class, there were assignments that asked to find kernels, and I would think for a long time about every vector that worked, and it wasn't until one of the last days of class that my professor said something, and that was that definitively the kernel of a transformation is calculated by the null space of the associated matrix, which makes it a lot easier to find. And we found the associated matrix in the last video. Now, most transformations have a matrix that reduces to the identity, so their kernel is just a 0 space alone. You might also want to record the dimension of the kernel, which has a name, the nullity of t. Similarly to how the kernel transforms into the 0 vector, the entire domain transforms into the range, which might sound familiar from algebra, where range is the scope of all the y values a function covers. But in this case, it is a new vector space, which is a subspace of what's called the codomain. If t is from v to w, v is the domain, w is the codomain, t of v is the range, and the inverse transformation of the 0 vector is the kernel. Like how the kernel of the transformation is equal to the null space of the associated matrix, range is the column space of the associated matrix. The dimension of the range is also very important, and it's called the rank of the transformation. And there's a fact in linear algebra called the rank theorem, or the rank nullity theorem, which states that the sum of the rank and nullity of a transformation is just the dimension of the domain. More specifically, if A is an m by n matrix, the sum of the nullity and rank of it are just n, the number of columns. Now, the rank of a matrix is a bit different. It is the number of non-zero rows left over after Gauss-Jordan elimination. There are some more terms that apply to these properties as well. A transformation is injective, or one-to-one, if there is a unique vector in the range for every unique vector in the domain. To show this, t is injective if and only if the kernel of t is equal to the 0 space, and therefore the nullity is 0. Transformation can also be what's called surjective, or onto, meaning that every vector in the codomain is covered by the transformation. To show this, t is surjective if and only if the range of t is equal to the codomain, and therefore rank of t is equal to the dimension of w. Here is a Wikipedia article on the subject, which gives you a nice little visual and leads to the third topic here, which is bijectivity. If a transformation is both injective and surjective, it's called bijective. Bijective transformations are invertible, which is to say that if t is from v to w, the inverse t is from w to v. Bijective transformations are also called isomorphisms, meaning that dimension of v is equal to the dimension of w. But that doesn't necessarily mean that v is equal to w, which is why we have this tilde over the equal sign. Because remember that the dimension of R4 is equal to the dimension of P3. If v is, however, equal to w, which means t is endomorphic, if it is found to be injective, it's also surjective, and vice versa. Rank works a little differently when you're talking about compositions, and requires that we understand the the minimum function. If, as we have here, if t is from R100 to R3 and s is from R3 to M4 by 2R, then the minimum of all those dimensions is 3 because it's 100, 3, and 8, and the smallest of those is 3. In general, if t is from u to v and s is from v to w, you'll always find that the rank of the composition t composed with s is less than the minimum of the rank of t and the rank of s, which is also less than or equal to the minimum dimension between u, v, and w. To specifically calculate the rank of t composed with s, it is equal to rank of t if s is injective. It's equal to the rank of s if t is surjective. And if that doesn't narrow it down, it is equal to the minimum between the rank of s and t if the rank of t is equal to dimension v or the rank of s is equal to dimension v, which is the middle dimension.